Living or going to school on the peninsula, we are surrounded by water, almost literally, right? To the west, we have the ocean, to the east, the bay, and to the north, we have the Golden Gate, which is not just the bridge, but also the water underneath it. We can see just how significant this situation is in our lives by the fact that nearly half of you included either the bay or the Pacific Ocean, or both, on your map project. But we also interact with water in smaller ways. I saw a lot of creeks, storm drains, sprinklers, and rain puddles on your maps too. These are all reminders that big or small, water touches our lives. So today we're going to start small with the nature of water to build toward a greater understanding of the hydrosphere. In this video, we'll begin our journey with water on the microscopic scale, meaning too small to see without a microscope. Then we'll link the properties of water to the hydrologic cycle, or the movement of water, before we talk a bit about water in the air, including humidity, clouds, and precipitation. So we've talked previously about how the hydrosphere is water on Earth in all forms. But before we can get into the kinds of water we're familiar with, like oceans and rain, we have to start from the very beginning by talking about water as a substance. And I'll try to do this without too much chemistry. So let's start with water as a molecule. A molecule is the smallest unit of a substance, so even smaller than a drop. We need a very powerful microscope to be able to even see them. On the right here is one way that humans represent molecules, but this is just a teaching tool. They're not really red and blue circles. Molecules are made up of even smaller particles called atoms. These are the building blocks of all substances. So in a water molecule, we have 2 hydrogen atoms in blue and 1 oxygen atom in red, which is why we call it H2O. So it's H2 for hydrogen and then O for oxygen. Atoms themselves contain even smaller particles, including protons, which are positively charged and found inside the big colored circles, and then electrons, which are negatively charged and represented by those little white circles because they orbit around the edge of the atom. So our water molecule forms by sharing electrons between the hydrogen and oxygen atoms. One side of the molecule ends up with unshared electrons and one side doesn't. So that means that the 2 sides of the molecule are also charged. We call this polarity, and the sides are poles, a positive and a negative pole. You may have heard the phrase opposites attract, maybe when people talk about human friendship, but this saying comes from chemistry. So water molecules have this tendency to attach to other water molecules, negative pole to positive pole. So these are called hydrogen bonds. And we start with talking about polarity and hydrogen bonds because these properties end up having sort of weird outcomes. They produce unique behavior in water compared to other substances. Our first weird property of water is called cohesion. Because water molecules form these hydrogen bonds between each other, that means they tend to stick to each other, so they cohere. The second is called adhesion. Because water molecules have poles, they also tend to stick to other substances that also have poles, so they adhere. And from there, we can just follow this chain of weirdness. So cohesion creates surface tension, this sort of thin skin on the water's surface. This is what causes water to become beads. Like if you spill a drop on the table and it forms a little dome, that's from surface tension. And then when we combine surface tension with adhesion, you get capillarity, which means that in narrow openings, water can climb upward against gravity. So this is like inside plant stems or rock cracks. And we can also see these properties in action through water's high heat capacity, which means the amount of energy required to raise the temperature of a substance. So to raise temperature, you have to get its molecules moving quickly. But because water has those hydrogen bonds keeping the molecules together, water takes a large amount of energy to heat up. So this is, for example, why water heats up slower than land. And last here is that water is a powerful solvent. Its polarity lets it pull apart other substances, eventually dissolving the material. And this also means that water found in nature often has other stuff in it, so like other chemicals, minerals, and nutrients. And that's why water tastes different in different places. Water on Earth is found naturally in 3 different states or forms. Of course, the most common is liquid water, and we're also familiar with solid water, also known as ice. We may be less familiar with water in the gas state, which is called water vapor. In this form, water is invisible and just becomes part of the air. Water can move between these states through what is called phase change. And this is a process that exchanges energy, called latent heat, between water and the atmosphere. So when water is heated up into a higher state, energy is absorbed into it, which leaves the atmosphere cooler. And then when water is cooled down into a lower state, energy is released from it, which leaves the atmosphere warmer. So the first two should be familiar. Freezing is when water turns from liquid into ice, and this releases energy from the water. The opposite is when ice melts into liquid, so the water absorbs energy from the atmosphere. Then when liquid water turns into vapor, it's called evaporation. And the opposite is condensation, when water vapor turns into liquid. And then the last two are relatively rare. Sublimation is when ice turns directly into vapor, and then desublimation is the opposite. So now that we know more about how water works on a really small scale, we can zoom out to how water works in the environment and how it interacts with the atmosphere. We call this interaction the hydrologic cycle, or the unending circulation of the water found on Earth. As we see in the bottom right, liquid water evaporates from the surface into the air. And then at the top, we see water vapor condensing into clouds and then precipitating, which happens as rain, snow, hail, etc. And then on the right, liquid water runs into larger bodies of water, like rivers, lakes, oceans, and so on. So this is a quick overview, but now we're going to get into it in a little more detail. So humidity refers to the amount of water vapor in the air. It's described in multiple ways, but we're going to focus on relative humidity. This is a measurement of the actual amount of water vapor in the air, measured in grams, divided by the maximum amount of water vapor that the air can hold at a given temperature. And this maximum is called the capacity. So this gives us relative humidity as a percentage. To give a comparison, we could think of liquid water and a cup. That cup has an amount of water it can hold, so its capacity. And then the more liquid you add to it, the higher the relative fullness. But with the air, there's no cup. The capacity is instead determined by the temperature. When the amount of water vapor in the air reaches its maximum, we call that saturated. So saturation is the point when relative humidity is at 100%. This can occur by adding more water vapor to the air or by decreasing the temperature of the air, which brings down the capacity. When the point of saturation is passed, the water vapor in the air can condense into liquid. And note here that I'm saying the vapor can condense. We'll come back to that. So temperature is important here because warmer air can hold more water vapor. The higher temperature keeps the molecules bouncing around, keeping them from condensing as easily. And the opposite, of course, is also true. Cooler air can hold less water vapor. So we've looked at saturation from the perspective of relative humidity, the amount of water vapor compared to capacity, but we can also look at saturation from the perspective of temperature. The dew point temperature, or simply dew point, is the temperature at which saturation is reached, and this depends on the amount of water vapor in the air. So by putting these two measures side by side, we can see that they're really like two halves of the same condition, the saturation of the air. So to back up a little bit, I said that when the point of saturation has been passed, water vapor can condense into liquid. But saturation is not enough to cause condensation, and this is because of surface tension. So surface tension, because of those hydrogen bonds pulling water molecules together, resists the growth of surface area. To grow, the water needs some other surface on which to collect to overcome surface tension. So this is where condensation nuclei come in. These are particles in the air around which water droplets can grow. And these can be any solid particle, really, including dust, smoke, pollen, salt from ocean spray, and even bacteria floating in the air. The water clings to these particles and the droplets grow. Really quickly, let's recall adiabatic temperature changes, meaning changes in temperature caused by changes in pressure. So warm air rises, it expands and then cools, which is adiabatic cooling. Cool air sinks, and then it compresses and warms, which is adiabatic warming. The reason I'm bringing adiabatic cooling back up is because it makes it easier for air to hit the dew point. And if that happens with condensation nuclei available, we get the formation of clouds. And I was hoping to fit information on identifying clouds by type here, but I'm trying to keep the video short, so I'll post something on Canvas. And so lastly, we have precipitation, which refers to drops of liquid or solid water falling from clouds. And examples include rain, snow, and hail, which are like little ice pellets. And so condensation into clouds is not enough to form precipitation. The tiny droplets of water need to join together to be able to fall, or else they just get blown around by the movement of air. So this happens in a couple ways. In warm clouds, droplets will collide and then form a bigger drop. So this is called coalescence. They coalesce into drops. In cool clouds, which includes clouds that are high up in the troposphere, some droplets will freeze into tiny ice crystals. Water vapor actually has an easier time attaching to ice than to liquid, and as the ice crystals grow larger, nearby liquid droplets actually shrink and then replace the vapor in the air. These crystals then either fall as snow or they melt into rain. In the next video, we'll continue with the hydrosphere by talking about oceans, ice, surface water like rivers and lakes, and groundwater. Thank you for watching, and I'll see you next time.